Yeah, hi, this is a lecture on random variables and discrete distributions. It's going to be a series of videos where we talk about random variables, expected values, and variance. That's same as the mean and the variance. The binomial distribution, the Poisson distribution, and a little bit about the hypergeometric distribution. So what is a discrete random variable? It's basically similar to the notion of a variable we talked about on that chapter on data analysis, except we have this new word random. So let me explain this through an example, why we call them random variables. The discrete random and RV for random variables arises in situations when the population or the possible outcomes are discrete or qualitative. Again, we talked about these in data analysis, so you want to review that material. Let's talk about this special. So if you toss a coin 3 times, then this would be your sample space. H, 3 heads, 2 heads and a tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, and tail, tail, tail on all 3 outcomes. Of course, if you remember, if we were to toss a 100 coins, that's going to be in the hundreds and trillions of outcomes that we even cannot count on a fast computer. It would take us light years to do it. So we want to simplify the problem. If you toss a coin, say 3 times, you're probably not interested in the order in which the head occurs, but how many heads occurs. Like if you are interested in how many defective items, instead of which item is defective, which item is not at any given time. So here we define this variable, we call it x, capital X, and represents the number of heads observed. Then the relevant events will be x equals 0, mean no heads, which is 3 tails, x equal 1 head, which means we have 1 head here in each one of these outcomes, x equal 2 heads, and x equal 3 heads. If you look at this simple example and see what's happening now, is instead of being interested in every possible outcome, you are interested in collection of outcomes that are mutually exclusive, they are disjoint, and there are fewer of them. So instead of having 8 events to worry about, I have 4. If I'm tossing 100 coins, instead of having trillions and trillions of simple events to worry about, I would be interested in 100 of them, or 101. So that's a big difference. So now we have simplified the problem significantly. So the relevant question is to find the probability of each of these events. Note that x, so now let's look at this random variable. It takes integer values, even though the sample space consists of heads and tails. Our random variable takes integer values. It's much easier to work with integer values than to work with heads and tails. So we basically convert the problem from sets to calculus, which is much easier for algebra. So here is the summary of this. A random variable is a rule that assigns a numerical value, as in here, to each possible outcome of a random experiment. So all these 3 random experiments were assigned the value 1, these 3 were assigned the value 2, and so on. The interpretation of a random variable is this. It's called random because the value of the random variable is unknown until the outcome is observed. So you don't know whether you're going to get 1 or 2 until you throw the 3 coins. Okay? It is the notation we use, capital letters X or Y, and so on. It is discrete because it assigns a finite or countably infinite number of possible values. So we have here 4 of them. We're going to talk about continuous random variables in the next chapter. So a quick definition of that now, just for contrast purposes, is that it has a continuum of values like height, weight, price, and so on. So each random variable has a set of possible values and probabilities, and the set of probabilities is called the distribution of that random variable, or probability mass function of that random variable. And that's the definition. The probability distribution of a discrete random variable x assigns a probability px for each possible value, such that, of course, probabilities have to be between 0 and 1, and they add up to 1. If we have small number of these values, we can tabulate them. So let's look at this example and see which one of the following defines a probability distribution. Well, let's look at the first one. I have 3 possible values. I have probabilities 0.3, 0.5, 0.2, so the probabilities are all between 0 and 1, and they add up to 1. So that's a legitimate probability distribution according to the definition. Let's look at this one. I have 3 values. Oh, I have a negative value here, so that even though they add up to 1, but I can't have negative values, so that's not a probability distribution. Here, oh, I have a negative value. That's fine, because that's an x, a possible value of x, not the probability. So all probabilities are between 0 and 1. That's fine. I'm going to add them up. 0.7 plus 0.2, 0.9. So it doesn't add up to 1. And that's the problem. So these don't add up to 1, and they don't have a legitimate probability distribution. Yeah. So only the first one is a probability distribution. Some comments on this. Discrete distributions arise when the random variable is discrete, when we're dealing with qualitative data, basically. Continuous random variables arise when the random variable is continuous, or dealing with quantitative data. In the first chapter on data analysis, we described a set of data, a sample, by dividing it into classes and calculating relative frequencies. If you remember, we did some histograms there. In the chapter on probability, we described a random experiment, theoretically, basically. That's the conceptualization of population in terms of events and probabilities of events. And we noticed here we had to deal with sets and their events and their probabilities. So here we describe a random experiment by using random variables, which take integer values. So we simplify the problem further and deal with probability distributions. And it turns out these probability distributions are very similar to these relative frequencies. Actually, the relative frequencies are estimates of these probabilities. Okay. Now, as same way we calculated sample mean and variance and standard deviation and data analysis, we can do the same thing for probability distributions. Well, I invite you to compare these values, go back to the group data and see how close they are. So the mean, or sometimes we call it the expected value of a random variable x. Random variable x is a representation of a population. We denote that by mu. So now we're dealing with populations, not with samples. So mu is the mean for the, or the expected value for the random variable x, and by definition it's given by this formula. So we take x, we multiply by p of x for each x, and we add up over all x values. Right? So sometimes people write e of x instead of mu for expected value of x, or mu sub x, the mean of the x random variable. This notation is used when you're dealing with more than one population. One you may call it x, another you may want to call it y, and so on. Okay, if x is a random variable with mean mu, then the variance is defined this way, and similar to against chapter 2, we take x, we subtract the mean, we square, and then we multiply by p of x, and then we add everything over all possible x values, and we call that the variance, or sigma square. So this is sigma square, population variance. Notation, people use sigma square or v of x or sigma square and sub x here. Okay. We also have for computations, this formula can be a little bit awkward sometimes, especially if mu is 3.261. There's a lot of fractions you have to add and subtract. It becomes cumbersome, and also gives us, more importantly, it can lead to round off error and propagation error. So this computational formula avoids that, and basically you compute the mean, which we did here, and once you compute the mean, you compute this part here, which basically you take x, you square it, multiplied by p of x, you add, and then you subtract the square of the mean, and that's your variance. And if x is a to compute the standard deviation, you just take the square root of the variance, and we can also get the standard deviation by taking the square root of the standard deviation in the computational formula. So that's the computational version of that, right? So let me go over an example here, and say we have this data here. We're going to start here, and so I have x takes, I think let me switch this, maybe I reverse this, but it's on the opposite side. Oh yeah, I have to start over. So x equal, say, possible values -1, 0, 1, and 2. I know p of x is equal to 0.2, say 3, 0.2, 0.3. Let's see, is this a legitimate distribution? Well, all the probabilities are positive and they add up to 1. So I want to find the mean and the standard deviation here. So to find the mean, I get x times p of x, and let's see, -1 times 0.2 is -0.2, 0 times 0.3 is 0, 1 times 0.2 is 0.2, 2 times 0.3 is 0.6, and if I add these, that's just 0.6. So my mean x bar, mu, dealing with the population mean, forget about that, is equal to, the formula is summation of x times p of x, and this would be equal, that's x times p of x, that's their sum, so that's just simply 0.6. Okay. Let's find the variance. To do the variance, I need x squared times p of x, which I'll do here, and let's do -1 squared is 1 times 0.2 is 0.2, 0 squared times 0.3 is 0, 1 squared times 0.2 is 0.2, 2 squared is 4 times 0.3 is 1.2, so the total is 1.6, and this quantity is the sum of x squared times p of x. So if I want to find the variance here, sigma square, I'm going to use the computational formula. I'd like to do that better. X squared times p of x minus mu square. I substitute here, oh, that's 1.6 minus mu is 0.6 square, so that's equal 1.6 minus 0.36, and that's gonna be equal to 1.24. So if I want the standard deviation, I simplify, it's the square root of the variance, which is the square p of x minus mu square, but I already computed this, so I don't need to do the whole thing. So this is the square root of 1.24, which is going to be approximately equal to 1.11. Okay, so that's an example which for this problem, and we'll I think we'll end it here. Thank you.